some of the other institutions that we worked with in Georgetown and Stanford and a slew of them. But what we're really going to talk about today, and probably no stranger, these workloads are no stranger to people in the room, but just to make sure that we set the table properly here, the reason that we're talking about running these types of workloads in the cloud is because what we've spent the last many years doing is trying to get more resources into the hands of researchers who can use them. And the use of AWS to do that is truly groundbreaking. I mean, it is going to be as monumental a shift in terms of accelerating science as Linux clusters or any of the other things were 15, 20 years ago and supercomputers were 30 years ago. And the real challenge is going to be to go harness them. And the reason that it's such a critical or such an important new development is because the nature of these workloads. These workloads are not standard enterprise. These are things that are big, unstructured data. It's the things that have run on the big workstations that people had in your offices or the clusters that were in the basement or wherever else it was. And it requires the tools and the applications that most people have never heard of, but that the output people have seen. So whether it's about hearing the advances in genomics relative to cancer, or whether it's crash testing, or some of the important work that's being done on the social sciences relative to big data, all of these workloads are ones that are handled by what we'll call technical computing, right? And what's really important about them, oh boy, builds, yikes, is that, and now I got to go back, hand puppets. Here's the reason that this is a problem, is that these are the fastest growing workloads for all of us right now, and whether this is the public sector or whether it's commercial. And so the demand for these from the research community and the R&D community is growing geometrically, whether you want to call it 25, 50, 200% per year. It doesn't matter how big the number is. It's growing faster than either the budgets to support them from an infrastructure perspective, or even more important, if people had budgets, it's outpacing the ability to contain these in the data centers where they currently exist. So even if people had a blank check to go build the biggest computers that they needed to and build out their own infrastructure to solve these problems, the fact of the matter is that no agency, no company, no university has enough real estate, power, or cooling to be able to support what are going to be the compute demands going forward. So this is not a problem that we're talking about that we're solving for one application tomorrow. This is about solving a problem that's going to face the research community, that we're going to become a victim of our own success. The easier we make it for researchers to use computational resources, the more they're going to demand it, and the harder it's going to be for them to supply what it is that they need. And if we're all here to facilitate science, we don't want that to happen. So that's what we're going to talk about. So the problem is that as that pace continues to grow, that stopping science is something that just, it can't happen. And so the best way to tee up what we're going to talk about today is, let me give you one example. This was an example from an AWS event. Last year, Novartis, pharmaceutical company, but it doesn't matter whether it's pharmaceutical or whether it's public sector, that this was a computational chemistry run off of an open source code. And what happened was, the researcher came to Steve Lister, who runs HPC globally for Novartis, and he said, hey, the great news is that I think that I've got line of sight to some very promising compounds, but I need 50,000 cores in order to do the run. Now, Steve had access on their floor to 7,000 cores. The challenge was going to be that even if he somehow parsed that out and did some other gymnastics in order to be able to get that particular workload to run, all other work at Novartis was going to have to stop for the days and weeks that would be required to go do that. So that was just a non-starter. AWS and Novartis and Cycle worked together, and long story short, 2 weeks later, we had been able to take that workload that had been running on bare metal, we ran it on AWS, and we took the science that would have been weeks to months to run and got it down to 11 hours. And the dollars to do it were less than $10,000. And so if you had taken that run and extrapolated it out to if somebody had had an open checkbook to build a system big enough to support that run, it would have probably been about $30 million to build a machine that big. And it would have taken a year and a half. And instead, we had executed against the problem in 2 weeks from the time we first started talking about it. So when I talk about this being game-changing technology, everybody wants to think that they've got game-changing technology, and most of the people here do. But this is going to be world-changing from the standpoint of being able to solve problems that scientists were afraid to approach before because they were limiting their own thinking to saying, well, if I only have 7,000 cores, I need to think in the world of 7,000 core problems. What we're really talking about doing, and what Dan's going to walk you through, is what the whole goal of last year's AWS Head in the Clouds challenge was. And last year at this time, Intel and AWS had said, hey, we would like to go find some problems out there that can only be solved by customers and vendors working together and attacking a problem that couldn't be solved were it not for the unlimited resources made available by AWS. And Dan and I have known each other for a long time, and we've been talking about a couple of things, and we thought, what a great opportunity. So Dan submitted an abstract, and it was accepted by Intel and AWS, and here we are today. And so it's really exciting to see all of these pieces coming together, but more importantly, coming together in something that's meaningful, not just to the technology and to the business model, but to something that's going to have a real impact on literally everybody in this room and outside of this room. So, just a very quick note in terms of what our piece of it does, so that when people say, well, okay, I get it, Cycle, but what exactly is it that you do? We are the software that sits in the middle of being able to orchestrate that workload. So if we have workloads that we're traditionally running on infrastructure, and then we've got all the resources that are made available to us by AWS, it is what we give people the ability to do is to take that workload, move that workload from bare metal to AWS, but then once it's on AWS, take advantage of all of the things that AWS has to offer relative to multi-zones, auto-scaling, error correct, all of the things that you need to do to ensure that just because you have moved it to the cloud, there's still no difference in the user experience. Because it doesn't matter how cool this is, if it's 10 times harder for the user to do, the user's not going to do it. So in a nutshell, what our software does is enables us to help you run those workloads on AWS and do it in a way that it is as unobtrusive to the user as possible. And that's what's going to keep science moving. So, just to wrap up, when Dan and I were talking about what could we go do together, the great thing about cloud and the lesson to take out of all of this is that it doesn't matter whether the challenge that you've got is enormous or it's pretty measurable and pretty finite. The great thing about cloud is that the best way to try it is just to try it. There's not getting a bunch of stuff in-house or any of those other pieces. It's taking your workload, getting it to run on AWS, and then running it. Because what you're going to find out is exactly how it works. And so the effort that goes into determining whether or not this is right for you is, percentages, many percentages smaller than it used to be in terms of figuring out whether there was a new way for you to tackle big problems. So, with that, I'm going to turn it over to Dan.
So I'm first? Yep.
You were first.
You're first.
There you go. Oop. It's a good transition.
Okay.
So there we go. Thank you, Dan.
Thanks, Tim. Okay, so so I'm going to talk about the project that we're doing here with the Amazon Web Services, Intel, Cycle Computing, and some others. I'll show you the partnerships in a minute. But basically, it's measuring some biomass in the south side of the Sahara at a very, very high-resolution imagery. So there's my email. There's my Twitter handle if you have nothing better to do. So I will correct one thing that Tim said, is that this idea really came from Dr. Sundar Lee, who's here in the front. He worked with a couple people at Goddard to come up with some of these ideas. So which button do I use?
Oh, it's the green. Oh, thank God it wasn't just me.
It's the big green one in the middle?
It's the big green one that has an arrow pointing in that direction.
Right.
There you go. And there's not a back button, so
gotcha.
don't over-click.
But there's not a back button, nor is there a rail. Okay. So if I go over, I'll just keep talking. Okay, so Tim talked about the Intel Head in the Clouds project, and this was a challenge that Sundar and the PIs at the bottom there, Dr. Jim Tucker and Dr. Paul Moran from University of Minnesota came up with. Basically, it's to estimate the carbon that's stored in the trees and the biomass in the semi-arid in the south side of the Sahara. Okay, so why do that? The reason you do that is, of course, to understand how much biomass is there, how it's changing over time, how much carbon it's sequestering, how much carbon it's uptaking, to understand potential for this area and its effects on climate change. Green button. Got it. Okay, the partners here. We had several partners here. Amazon, of course. Intel is up the top. They're providing some services. and also the funding for some of the resources. Amazon, of course, is there. We wouldn't be talking at this venue if it wasn't for Amazon to provide all the resources. Cycle computing that Tim talked about. I'll show you how all this fits together in a minute. The Climate Model Data Services at NASA Goddard is providing the data support for the NGA data. I lead the NASA Center for Climate Simulation. One thing that Tim talked about was, why can't you just do all this in an HPC environment? We're trying to bootstrap a lot of data analytics and data analysis in HPC environments. We've been doing it for a long time. What is happening is the models and the observational platforms, the remote sensing platforms, have been creating so much data over time that those requirements are growing so dramatically that we can't keep up with both the data analytics requirements as well as the traditional HPC requirements. So that's why Amazon and other resources are very beneficial. And of course, we're getting a large amount of support from the NASA CIO's office, who's very interested in seeing this work. Okay, so what's the area of interest? This is Africa. You can see the shaded area or the outlined area of interest up at the top. The middle shows about 1,600 stripes across there. There was about 20 terabytes that we had got it already. This is where we want to eventually get to. You can see once we fill all those stripes in, those are images from NGA, and I'll talk more about that in a second. Once you fill all that in, that's about 80 terabytes. Okay, so that's where we want to eventually get to, and we're getting all those 80 terabytes in at Goddard. Now this is NGA data, so it's not classified because we're not looking at areas of active conflict, but it is sensitive. We've licensed it for use for NASA science projects. So we can put it in Amazon and use it, and then we'll basically remove it after that. Here's the fleet of Digital Globe constellation. These are all archived by the USG, and we have license to support some of this. Now, this is what we know that Digital Globe has, and right now the highest resolution images we're getting is about 0.4 to 0.5 meter resolution, which is pretty impressive. I am sure over years of time we are going to get higher and higher resolution images, and I'm sure they already have those right now. Okay, so what can you see at 40 to 50 centimeter scale? Okay, so here you show two pictures. One is just the black and white picture. The other is more of a multispectral image with an NDVI, which is a vegetation index. What you see on the left is trees and shrubs. That's what we're going to count. We're going to try to count trees and shrubs. If you count the trees and shrubs, you know how big they are, then you get an estimate for the carbon uptake. On the left, you'll see some images there, and if you have a keen eye, you can compare it to the right, and what you'll see, the images on the right, which is the vegetation index, are slightly different. If you look at the left, you'll see some very, very dark regions around the trees and shrubs. Those are shadows. So you have to get rid of the shadows in order to actually come up with a vegetation index. Otherwise, your trees and shrubs are going to be much bigger than they actually are. So it's a pretty decent process that you have to go through. So we're going to use a small area of Africa as the test case right now. So it's about 1,600 total scenes, and so you say, okay, there's let's see here. For this test case, we're only going to use about 3,100 of those scenes. So it's not too many scenes. But let's start adding up the math here. So each scene is about 30,000 by 30,000 pixels, a lot of pixels. We break that up into about 100 tiles each. Okay, and currently all that data is stored within the NCCS, and we actually have that data stored in Amazon. We'll show you how we get that there in a second. And if we succeed, this is where Jim Tucker and Paul Moran and probably Sendar want to go and do as much as possible. We'll talk about how it's going to grow in a second. The processing requirements for each individual image are actually relatively small. Okay, so we were able to test this out on systems that we have at Goddard. It's a very small, one core, 2 gig of memory, and you can process each tile in about 24 minutes. Okay, so start adding up the math here. 24 minutes per tile, and all the tiles add up to be about a total compute hours of about 124,800 compute hours, okay? And if you say, let's scale that up to about 200 virtual machines in Amazon, assuming some overhead here and some making sure you've got some extra images out there, it's about 1 month, okay? So when you talk to a scientist and you say things like, okay, what are your requirements? And they start talking about data and they start talking about science, and then you ask them the question, well, what's your time requirement? Invariably you get the answer, immediate. It's got to be done now, right? It's all the time. Okay, so we're going to get this done hopefully once we get everything set up, and and I'll tell you how we're setting it up in a second. In a month of time. Okay. Jim Tucker's already on to the next thing. He's already said, let's do this country and this country and this country, and I'm saying, oh, slow down. We need to get this done first. But the thing is, this 3 terabytes or this 8 terabytes of data that we're going to measure here is just the tip of the iceberg. Over the next several years, The plan is, and it's not, I won't say it's a firmed up plan all the way, so you may come back to me in 6 months and say how's that plan going? It may have changed. But if we enact this plan with NGA data, we could have as much as, over the next few years, 8 petabytes of data. Okay, so that's 1,000 times of what we have now, and we want to process that. Okay, so now we're talking about 1,000 times 1 month. Okay, there's no way that scientists can do that, right? You just don't get any relevant data. As soon as you get the answer, your data is basically obsolete. Or you can either scale in time or you can scale in virtual images. So now we're talking about 1,000 times the 200 virtual machines. Okay, that again is a supercomputer, just like Tim was talking about. If you go out and buy a virtual machine or a supercomputer with 200,000 cores in it, you're into the tens and tens of millions of dollars. Input data and output data, we talked a little bit about this. Input data is now actually relatively small, about 8 terabytes, 3,100 scenes, just for the test case. Again, that's going to scale up dramatically in the near future. The intermediate products, we don't actually know how much they are, but we're going to bring it back. Our estimate is about 25% of the output, of the input will be about the output. So if we take 8 terabytes input, we're going to generate about 2 terabytes output. So it's not too bad. Again, this is classic data analysis, right? You start with big data, end with small data, which is exactly sort of the opposite of HPC. In HPC environments, what you do is you start with small data and end up with big data, if you think about it. And the output's going to come back to the NCCS. So for those of you who really want to geek out with some specs of the system, it's really not that hard. One core, 2 gigs, Linux system. These are inherently parallel processing images. So what we need is the capability that Cycle's giving us to have the batch queuing system in there, to have the data movement in there, so that the scientist doesn't have to manage all these virtual systems. They just submit to a queue, and the queue manages this and fires up the images and takes care of all that stuff. So this is what it looks like. The workflow is pretty simple. Up at the top in the green, you have the NGA data that's coming from University of Minnesota, from the PGC. It's coming into our shared storage system. We have a little private cloud here. So this is really a hybrid cloud approach. We can do some processing in our private cloud, and then when we want to burst out, now we got the processor working, okay? And it's working to some extent. And I said 24 minutes. That's where Intel's going to come in, and it's going to help us take that 24 minutes and get it down to, a few seconds. Okay. So even if they do take the 24 minutes and get it down to say, let's be really optimistic and say it's down to a couple, 3 minutes. We're going to do, when you step and say, okay, now I want to do 1,000 times that, it's still pretty significant. Okay, so you got in the private cloud at the NCCS, we've got the data management or the data man software there that helps us move data in and out of Amazon. You go to Amazon and we have the cycle computing system there with the batch queuing system. And what happens is you submit a job to the batch queuing system, the data is stored in S3, the batch queuing system fires up the VM, grabs the tiles that you want. There's a little script that goes through the tiles and says, okay, here's a tile that hasn't been processed, copies that to the local data, the VM processes that data with its stream, stores the data back, we move the data back to the NCCS. So this is all the kind of how it all fits together. So our timeline is rather lengthy when it comes to cloud projects, simply because we didn't understand the cycle computing software. And the other requirement that Tim and I have kind of come in and laid on top of this is we don't want this just to be a one-off thing. We want to do this that's more sustainable. We don't want to do this just for NGA data. We want to make this capability available for a lot of other NASA scientists. And whenever you get a CIO's office involved, things take a little bit longer than you want. So just keep that in mind. The other thing is scientists are there any scientists in the room? Excellent. So we can talk about that. So a lot of former scientists in the room, right? Yeah, that's right. So scientists are inherently optimistic about their processing, where they are in their application development and their processing capabilities. So when we started this, Jim said, oh, we're right there. We're ready to go. And then we start having the tag ups, and, stage 1 of the processing, we're working on that. Okay, well, stage 1 of how many? Stage 1 of 3. So, okay, we're up to stage 2. We got stage 2 running, but he's still working on stage 3. So you have to still, when you talk to scientists, pull them out and get their requirements and figure out exactly where they are, because they are inherently optimistic about what they're doing. So we're still honing in on that application. So why use this? We've talked about this in several ways. So one of the biggest reasons is with our hybrid cloud approach, we can burst. So if a scientist does come to us and say, okay, Dan, how much resources do you have in your private cloud? Okay, this is what I need to process. Can you get this done within the time frame I need, which is maybe 2 months? And we can say, yes, we can allocate resources so you can get that done in 2 months. Or they may come to us and say, we have this huge data set. Can you get it done in 2 months? And we say, we don't have the resources for that. If you want, we can trigger this. Now, this is where the scientists can come to us and say, okay, yes, I would like to do this, and here's some funding, and we'll pay Amazon to do this, and we have this capability set up, and suddenly they can get their job done in the 2-month time frame that they want, which I think is really a neat concept. Okay, so there's many, many people to thank, and I'm sure I've left people off. I usually do this in a word cloud so people can't find their name, okay? And they also can't find whether they're not up there. I did that one time, but somebody said, you missed my name, so I actually don't know if he was right or not. So there's a number of people at NASA that are doing this across Goddard headquarters with Dr. Sundar Lee, who's here in the front, and at Ames, the CIO's office people at Ames, our university partnerships, cycle computing. There's a number of people. Tim's like me. We're higher level managers now, and I have known Tim for quite a while, so it's been great working with him. The cycle computing group has been fantastic. They are very, very responsive to what we've been asking for. The AWS, Jamie and Jeff have been great. Intel partners have been awesome. They're helping us get everything set up, and ultimately we're going to give them the code once Jim's done with it so that you can optimize that. So I think that's my apologies if I missed anybody, and I think that's it.
Great. Thank you. So I don't have any slides. I just wanted to talk a little bit about how we're helping out, and Dan really set me up well with what Intel can bring to the table here. So one thing to keep in mind when you look at cloud, a lot of people say, well, then it's all about the cloud. Hardware doesn't matter anymore. And I'm here to tell you hardware does matter. The reason is when you start looking at these kind of high-performance computing workloads, big data workloads, optimizing your code for the infrastructure on, whether it be the bursting capabilities, the turbo boost capabilities of the CPU, the memory to CPU ratios, allows you to get the best out of the systems. But also when you start to look at the application itself and say, well, how can I optimize this application for the parallel nature of the architecture I'm going on? How can I take advantage of some of the instructions in the CPU like AES&I and like AVX instructions that can help you pipeline certain aspects of your application is how you get from 24 minutes down to 24 seconds or whatever we're going to be able to get for you. 24 seconds is a goal. And we've seen this time and time again. For those who are familiar with the TerraSort, which is one of the key benchmarks for big data, we were able to take a look at not only the CPU it was running on, but the infrastructure and optimizing the code for the Hadoop infrastructure that was running it. And we're able to take something that was a 4-hour process down to 4 minutes. And that's why we think we can get to these kind of optimizations, because making sure you optimize your code for the right infrastructure and take advantage of features that are already there available to you will get you far down the line. And nothing against the application developers in science communities, but let's face it, they're scientists, not engineers. A lot of times they're going to try to get the code to work, and that's great, and that's the first step. Where Intel comes in and helps afterwards is we help them optimize their code to take full advantage of the platforms they're working on. So I just wanted to put that out there, is that as you look at bringing your applications into Amazon Cloud, keep in mind that you're going to be running on an infrastructure that you can take full advantage of. Optimize your code, optimize your infrastructure, work with partners like Cycle Computing that can help you to take advantage of the right class of system for your workload so you get the best bang for your buck. Thank you.
Thanks, Steve. We're gonna open this up for questions, but I wanted to tag on to one thing that Steve was talking about, and this is it's very important, especially if either you are responsible for the work or the people or the folks responsible for the work are coming to you saying, I need help. The light bulb that is starting to go off for the people who are executing against these applications is that in the cloud, actually, if you have a performance-dependent application, hardware actually matters more than it used to, because in the old days, not the old days, what, a year ago? Yeah, exactly.
Those are old days.
Actually, I do say, for the record, Sundar, I apologize for having given Dan credit for everything there, but having been a vendor to Dan for a number of years, I just got used to giving him credit for everything great that happened. Exactly, and that one time when we would roll clusters and stuff into their data center, one time somebody asked, how Dan and I know each other, and I said, well, I did a lot of the heavy lifting for Dan, and they were like, oh, do you write code? And I was like, no, literally. I was the biggest guy in the room, so I did the heavy lifting for Dan when we didn't have the dolly to get the racks moved. So, but what has happened is that all of a sudden people are starting to understand that, wait a minute, if this machine that we bought, this supercomputer that we bought, say it was 3 years ago, absolutely had the latest technology with the latest Intel processors in it 3 years ago, that machine is still incredibly viable for the science that it's serving. But for somebody who now wants to run an application that is performance dependent, that they want to run on the latest core that's available to them. And the latest core is actually available on AWS. And so that the faster that, that we work with Intel to tune and optimize the applications that are out there on the new cores, the faster we get that into the marketplace and the faster it becomes an incremental productivity tool for the people who are using it. And when you hear Dan talk about computational requirements that just get staggering in terms of thousands of hours, hundreds of thousands of hours, millions of hours, that's where performance tuning and optimization matters. It may not have mattered as much before if you were running on a 300 node cluster, but if you're now going to run 300,000 hours or on 3,000 servers, a 15% performance enhancement makes a big difference, not only in wall clock time, but also in the dollars that you're spending, because remember, that's the value of AWS, is that you're paying for it when you're using it and you're turning it off when you're not. So the faster you can turn it off, the better it is for you and the better it is for your scientist. And so what's going to have to happen in all of this is that there's going to be a tighter collaboration between the vendors that you work with over time than ever happened before, where you could just kind of get it and plink around with it on your own. So if you start down this path, I would encourage you to reach out to your Intel person, your AWS person, your Cycle person. Make sure that they're all in the loop. And so with that, we have a few minutes left. Does anybody have any questions about the science, the process, any of the other pieces that went along with it?
Not that we can see.
Say what?
Not that we can see.
Right, exactly. Just throw a shoe. I think I see something. I sense movement. Yeah. Sure. Hey, Jim.
Reading over your spec sheets and looking over the cycle server and the submit one capabilities, that's in play here, right?
Mm-hmm.
So I came in a minute or two late. You may have discussed that, and I missed some of that. But when Intel's talking about the ability to optimize code, and when you talk about bursting, and then you have, right, your hardware is not hardware. Like you said, x86, you got this heterogeneous variety of compute, and you want to obviously leverage it, fast, on demand, flexible, and the way it talks here for the bursting capability, be able to just have that hybrid capability. Maybe I could use some of the HPC capacity, and I could use some of the cloud, and that's what we're talking about, right? Optimize any combination thereof. True?
Yes.
Okay, so in that regard, what's the architectural stack look like this? There must be a methodology here, because it doesn't sound like it's submit one alone. This thing, oh, there you go. They want this thing to be configurable, right?
Right.
So that you could do what you're doing, not, oh God, I got to get the Intel dies in there to do some customization of this and that, because that's not fast. So do you guys have a methodology that you've developed in an architecture stack behind how you do this?
Want to go first?
Sure. So
Yeah.
for us, it's pretty simple. Okay. And architecture stack is actually on Amazon, very, very easy. So we have if you want to start with the Linux system, there is a Linux system image that we've created that has all the tools that is needed, right? And so if, for this particular case with NGA data, then the cycle computing software, which is really the batch queuing system, will grab that image, fire it up, and there's some scripts that we've developed along with Cycle that can go through the S3 bucket to say what images haven't been processed and bring it in there. So it's actually, they're somewhat dependent on the application, right? But you start with a fairly simple software stack that's in Amazon that can be reproduced. This same image could be reproduced for Landsat processing, for example, or Modus processing or other types of processing. It's not that different. And so we start with a simple building block that can be reproduced fairly quickly, if that makes sense.
And then the process that we go through is, once they get something like that up and you want to then scale it, is where, working with Intel, we can help tune that application that you've got up and running. You figured out the right stack for it, the right dependencies, is then when we can tune it to be able to take the full advantage of both the infrastructure and the hardware CPUs that you're on today, and also help to future-proof so that you can, when the new CPUs come out, you're able to take advantage of that as well. And then in certain cases with some industry ones, and I know you mentioned the one with Novartis and some of the genetics research, we've taken a proactive stance to go out and help some of the key tool sets like GTK and others that are used in genomic research and optimize them out of the gate without waiting for someone to come to us.
Does that answer your question? You got more.
It gets there, because what I'm looking at is there a, a reusable,
Yes. So, yep.
yeah, and again, I'm not saying customizable, reusable, configurable.
Yeah.
Is there something out there open source
Mhm.
for sharing that you can look at?
Well, typically what happens with us is that we've got now about 50 workloads that we've migrated over, and that's part of what we share those with customers, because the whole point is to speed up the process and learn from the people that came before you, right? And just to finish out what Dan and Steve were saying, what we're really doing is we're taking that product, which is really theirs, and then virtualizing the entire workload and moving it and orchestrating it. Because how many of us have been through the conversation where somebody comes in and says, hey, I can solve your problem in half the time for half the cost, and all you need to do is totally blow up your application, recompile it, and rewrite it, and then it's going to be awesome. And the reality is it's just not going to happen. And so the great thing about having software that's written by people that started out as users is that we know that that's just a non-starter. So the whole game is, how can you make it easy to move that workload as is, but then optimize what can be optimized, virtualize it, orchestrate it. And then what we do is we've got libraries for all of those workloads that we've done that for, and that's what we would share.
Yeah, so the scheduler that we're using out there is an open source scheduler.
Oh, right.
Okay. And so the orchestration software the Cycle has is their software that can do the data movement, but also do the orchestration with the batch queuing system to fire things up, but also to have your look into what's happening as jobs are running.
And just to finish that off, for the infrastructure components that you want to deploy into that virtualized box, like the Linux, the schedulers, big data stacks like Hadoop, Intel has been working for many years as one of the key contributors on those open source initiatives to have them optimized to run on Intel architecture. So if you're using any one of the standard open source toolkits or projects, odds are they have been optimized already or are in the process of being further optimized by Intel proactively.
Right. Did I see another question back there?
Yeah.
Another hand?
Hi, I worked in the Office of Science as a contractor, cybersecurity. I'm just curious to ask, the national labs have their high-performance computers, and have they done benchmarks with Amazon to see who's faster?
Well, so my good friend Jamie Kinney's in the room from AWS. So Jamie, why don't you take that question?
Yeah, there have been a couple of benchmarks a few years back. I think just before or just as we were launching our new HPC instance types, this was the Sandy Bridge processors at the time. And I think the benchmark, this was part of the Magellan report, looked at the relative performance of some of the capabilities that already existed within the labs compared to our pre-HPC instance types. And so I think the benchmarks, because they've taken generally 12 to 18 months to be developed and published, to reference the earlier timeline that we saw in the presentation here, they haven't always reflected the capabilities that existed as the report was published. So we've seen a number of benchmarks that haven't been formal benchmarks. I think they've been part of cycle computing case studies. A number of other ones that we've done with our customers. Had a very recently successful WARF run, for example, that outperformed some traditional InfiniBand backed clusters. So I haven't seen recent benchmarks publicly available that show kind of an apples to apples comparison, but we'd be happy to provide a research grant for somebody who wants to run a benchmark and see what their specific code looks like on our platform.
In NASA, we did benchmarks quite a few years ago, so it's probably been 3 years ago prior to the HPC instances coming up. And what we found is, of course, for some of the large-scale applications that we're doing, the MPI-based, the very, very, very highly parallel applications, it just didn't make sense. So that's why we turned our attention a lot to the data analytics side of things. So we want our HPC systems within NASA to focus on those big parallel applications that are going to generate huge amounts of data, the big simulations, the big global climate simulations at very, very high resolution. That's going to run at 10, 20, 30,000 cores. And then we want to take the analytics that's being done that's being a very inherently parallel analytics, where somebody's going to come along after that big nature run, and is going to say, let me find every hurricane that I can find, or let me find every mesoscale convective system or every atmospheric river or things like that, and characterize that. That's very inherently parallel and very choppy. That's the type of stuff, the analytics, that's growing so fast for us that we can't keep up with that and the HPC stuff, and that's where hybrid clouds for us, bursting into Amazon, will really be beneficial. Is that good?
Yeah, I agree with that. Completely agree with that, Dan. And I think we see, Amazon sees our services as a perfect complement to the resources that you might find at Pleiades or another tightly coupled system. Another common application that we've seen is to develop and test on a cloud environment so that you can iterate frequently. Maybe have 10 different clusters trying different ways of optimizing the code, and then run it at scale for the tightly coupled simulation.
Yeah, good point.
I think it's important that we solve the right problem. And the problem that I believe that we're solving for right now is that Linux clusters were a great alternative to monolithic supercomputers because it gave you flexibility, it gave you a number of things that it was a boon for research because it made compute more available to more researchers. What's happening now is not that we're trying to become supercomputers. It's that what happened with these Linux clusters was that since many organizations, whether it was universities or government, decided, well, the Linux cluster is the best happy medium that we've got. It can serve the broadest community. That what that means is that you've got a lot of applications. The broader your user base, the more likely it is that you've got applications that are running on a very sophisticated system that shouldn't be running on that system. And when you ask a scientist, they won't tell you what the wall clock time of their job is. They will tell you how long it took to get back. So it doesn't matter if the job took 4 minutes to run, but it sat in a job queue for 8 hours. The person that submitted that job believes that that job took 8 hours plus whatever the wall clock time was. When we submit a job to AWS, that job starts running as soon as we hit enter. Right? So even if there is a performance discrepancy between how that job would run on AWS and how it might run on the internal system, invariably, especially for the workloads that we work with, the user gets their data back faster, which is ultimately the job we're here to do. Was there another question over on that side of the room, I think?
Yeah, hi, Philip Southam with NASA JPL. So this current project that you're on, was it Greenfield, or was it basically enhancing a sort of already existing, quote unquote, legacy workflow or process in place?
That's a good question. Sender, would you say this is pretty, there wasn't really something, it was a thought. It was a science thought that was put in a proposal that did not get funded. And so from that, the feedback was go do some of this first and then come back with a more firmed up proposal. So it kind of started that way. And that sort of burgeoned into a huge concept centered around NGA. When we began to talk about NGA with a large number of other scientists, a lot of people said that would be great data for NASA to have. So it's kind of burgeoned into something quite large.
So one of the reasons why I ask is we have some existing scientific compute problems that were built on a fairly sort of legacy way of doing things that we're looking at bursting out into the cloud.
Yep.
But it's not to address the problem that you said, which is I can fix it, just rewrite the whole thing. It's, how did you go about, or how would you suggest going about sort of that engagement of moving sort of legacy systems that are sort of relying on certain things to always be there versus accommodating more elastic compute resource sort of workflow?
Sender wants to say something.
Right. So let me kind of address that question. So in a traditional funding model, the scientists write a proposal, and we put together a review panel and think about and evaluate this proposal. And a lot of time, the panel will say, "Oh, this requires tremendous amount of resources, and you can't do it. It's not ready." All right. So and this is the case. The proposal, the idea is really interesting, but the panel just feel NASA's not ready. And last year at this symposium, Intel offered this head in the
clouds.
head in the clouds, opportunity. We jump on that, right? So this is a perfect kind of a use case for cloud. You can rapidly try something new, put some new workflows together. We didn't have this entire pipeline. It wasn't ready, and we just say, okay, let's prototype, let's do it in the cloud. So, AWS and Intel offered some fantastic opportunity. We just take advantage of that. So thanks to Intel and Amazon. Right?
I cannot think of a better drop the mic, big Vegas finish to that. That's like, well, that's all right. Yeah, I appreciate that. Well, I forgot about you. I mean, all you're doing is a little payback. It's all good. No, and I would just, the other thing that I would finish up by saying is that Dan had mentioned that this, in its final iteration, was really a big data challenge, or we were addressing a big data challenge, and it was also hybrid. I can guarantee you that if we'd started this project saying, let's go do something that starts as HPC, but it's really a big data problem, and we'll also incorporate hybrid cloud in there, we would have never finished it, right? Instead, what we did was we just lined up on the problem. Bunch of smart, motivated people got behind it, said, let's just keep going, and then at some point we'll stick our head up and we'll see what it is that we just built. And so that's the guidance I would give for anybody that wants to head down this path, because it's the easiest way to make progress is just focus on the problem, because the tools are there today to be able to address it. So I think we're out of time. I don't want to hold people up from getting to their next events. We'll certainly be around for questions afterwards, but thank you very much for your time and your attention.